We've got two coils wrapped around this little cylinder here. The first one's got 20 turns, the second one's got 30 turns, and they actually would both have the same area if they're going to be coaxial along the same cylinder. They'll actually have the same area, so that's nice. And we're given the current 1 in terms of time, and we're looking to figure out what the induced current is in coil 2, and the direction as well. So we should be able to come up with, if we have the EMF in coil 2, that would be equal to the negative mutual induction times the time derivative of the current in coil 1. So all we need to do is figure out the time derivative of the current and the mutual induction, and then we'll have at least the EMF, that would be the voltage in this. We'll have to figure out what the current is a little later. But we can figure out mutual induction, and we should have a shortcut to figure out if they're coaxial coils, meaning they have the same center, the same origin, essentially. Well, we can actually use a shortcut by saying it's mu naught times N1 times N2. These are just the number of wraps. And then this is the cross area, like the mutual area between them. If this one was bigger and that one was smaller, it'd be the smaller area. And then we're also going to divide that by the smaller length. So when you do that, then you'll get the mutual induction. So then we could just plug it all into there. Let's go ahead and try to do that. So mu naught's going to be 4 pi, and even -7, and then N1 is just going to be 20, and 2 is going to be 30. The area is going to be pi r squared, pi, and then 1.5 centimeters squared. And then we're going to divide that by the smaller length, which is 1.8 centimeters. All right, so that's going to be the mutual induction that we could definitely plug into the calculator. It's going to have units of henries. And then we're going to want to sort of plug it into that equation, figure out the voltages. But I guess we'll do this one step at a time. This is going to be quite a big number. So we'll say 4 pi -7 times 20 times 30 times pi times 1.5 using -2 squared, and then divide that by 1.8, -2. I'm gonna mess up one here. Oh yeah, the pi's. Sometimes the pi's, you have to separate them out in these calculators. Pi squared. All right, so then we have a mutual induction of 2.961 -5, something like that. This is in henries. So let's plug that into this thing. So we'll have the EMF in 2 is going to be equal to -2.96 e to the -5 times the time derivative of I. So we're asked to graph this. I'll try to do that right here. We got 1 second, 2 seconds, and 3 seconds. Don't worry too much about what that is. So in the first case, we're trying to find the negative time derivative of this. If you plug in these points, you should notice this is a slope of -15. And at this particular location, you'd have a slope of -5. So those would be the two slopes that we're going to want to use, and we're just going to multiply them in here. So within the first little section right here, from 0 to 1, let's figure out what that would be, -15 over here. And so we would say -2 points, and here I can actually go back to what we're, exact answer, right? And then we'll just say times 15. So that would be the voltage going through this coil, but it's not the current yet. Let's remember Ohm's law. Ohm's law. I equals V over R, the voltage over R. So if you want to find the current, you have to divide the voltage by the resistance. The resistance is 2. So let's divide this by 2. If we divide this by 2, then we'll get the I2. All right, so in this particular section, we have 2.22 e to the -4 amps, right there. And then in this section, because the current's not changing, this is a slope of 0. You multiply them there, you'll get 0. So in this section, we actually have 0 current. I'll make this graph in blue just so that we have slightly better visual. And then for the last section, all we're going to do is essentially make the same equation here. Remember that this is the resistance. We're using this equation. But instead of negative 15, we'll use this. I guess we'll just go 2.96 e to the negative 5 times 5, and then we'll divide that by 2. So that's our next answer right over there. 7.4 e to the negative 5. It's very small numbers. There we go. So, using Ohm's law and the induced EMF and the mutual induction, so we were able to find that. But we also need to figure out what the direction is. And if we note this, keeping in mind that our currents are decreasing, the current is going into, if we got to use the right-hand rule here, it's going into the surface here, and that means that the magnetic field would be pointing to the left. So, that being said, if the magnetic field is shrinking, then that would mean we want to replace that magnetic field with the current in there. So, and therefore, that would also be doing the same direction. So it would going into the wall here, because that would replace what was just lost out here. So if you were to follow that across and you kind of come down through here, I do believe that would take you to the right through the resistor. So that would be how we can get these answers.